Most people never question the color of the ocean. It is one of those features of Earth that feels permanent, almost beyond examination. The sea stretches across more than 2/3 of the planet, reflecting shades of blue that have become so familiar they seem inseparable from the idea of Earth itself. Children draw blue oceans without thinking. Astronauts describe a blue world floating in darkness. Entire civilizations have lived beside blue water for thousands of years. It feels eternal. Yet, some of the most surprising discoveries in modern science begin with something that appears too obvious to question. Imagine standing on a shoreline billions of years ago. The waves still move with the same steady rhythm. Horizon still stretches endlessly into the distance. The wind still carries the scent of salt and water. At first glance, the scene seems familiar. Then the color becomes impossible to ignore. The ocean is not blue. Across the surface spreads a deep red hue, dark in some places, brighter in others, as though vast quantities of rust have dissolved into the sea itself. Under certain skies it might appear crimson. Under others, almost copper-colored. The effect is unsettling because everything else seems recognizably Earth-like. Yet the most familiar feature of the planet looks completely wrong. For a long time, such a vision would have sounded like science fiction. After all, oceans are supposed to be blue. That is what experience tells us. That is what photographs show us. That is what every generation has inherited from the one before it. Yet the deeper scientists began investigating Earth's distant past, the more evidence emerged suggesting that our modern oceans may represent only one chapter in a much longer story. A story far stranger than anyone once imagined. Hidden within ancient rocks are clues that refuse to fit comfortably within the world we know today. Strange formations appear in places that were once covered by water. Chemical signatures preserved for billions of years hint at environmental conditions unlike anything found in modern seas. Certain layers of stone seem to describe an ocean operating according to entirely different rules. These clues appear disconnected. A mineral deposit here, an unusual rock formation there, chemical fingerprint buried deep within ancient crust. Individually, they revealed very little. Together they began suggesting something extraordinary. Perhaps Earth's oceans were not always blue. Possibility creates an uncomfortable question. If the oceans once looked dramatically different, how much of the familiar world is actually temporary? Humans often imagine the present Earth as the standard version of the planet, as though today's conditions represent the natural state of things. Earth's history stretches back more than 4 billion years. The world has changed countless times during that vast span. Entire landscapes have appeared and vanished. Atmospheres have transformed. Continents have wandered across the globe. Life itself has repeatedly reinvented the planet. Perhaps the oceans were no exception. The mystery becomes even more intriguing because these ancient red seas would not belong to some alien world. They would belong to Earth itself, the same planet, the same oceans. The same world that would eventually give rise to forests, animals, civilizations, and eventually us. Somewhere in that distant past, the ocean may have worn a completely different face. How long did this strange era last? Forces could turn vast bodies of water red. What kind of life survived beneath those unfamiliar waves? Perhaps most surprising of all, some researchers now believe this was not merely a local phenomenon affecting isolated regions. The evidence increasingly points towards something much larger. Enormous portions of Earth's oceans may have shared these unusual conditions at the same time. If that is true, then the red ocean world was not an exception hidden in one corner of the planet. It may have been the planet itself, and that raises an even deeper mystery. If no human was there to witness those vanished seas, how can anyone possibly know what color they were? The question seems almost impossible. If the oceans of the ancient world vanished billions of years ago, how could anyone know what they looked like? There are no photographs preserved from deep time, no written records, no eyewitness accounts waiting to be discovered. The waves that rolled across those distant shores disappeared long before the first animal walked on land, before forests covered continents, before humanity existed even as a possibility. At first glance, the mystery appears unsolvable, and yet Earth has a habit of keeping secrets in unexpected places. The evidence was never hidden in the water itself. The water is gone. Instead, it survived in stone. Across several continents, scientists have found ancient rock formations that seem ordinary from a distance. Mountains rise beneath changing skies. Cliffs stand exposed to wind and rain. Layers of stone stretch across landscapes that appear timeless. Inside those rocks exists a record far older than the mountains themselves. They are fragments of vanished worlds. Long ago, many of these rocks rested beneath prehistoric oceans. They formed slowly, layer upon layer, as particles settled through ancient waters and accumulated on the seafloor. Over immense stretches of time, those sediments hardened into stone. Continents shifted, oceans retreated, mountains rose. Yet portions of the record remained preserved. To scientists, these formations are more than rocks. They are pages from a planetary diary. Each layer contains clues about the conditions under which it formed. Certain minerals appear only when specific environmental circumstances exist. Particular chemical patterns reveal information about ancient water. Even the arrangement of materials within a rock can tell a story about a world that no longer exists. What makes the mystery especially intriguing is that the same clues appear repeatedly. Again and again, researchers encounter unusual deposits rich in iron, vast quantities of iron, isolated pockets but enormous formations stretching across regions and, in some cases, entire continents. Some of these deposits are so extensive that they have become major sources of iron ore in the modern world. Decades, geologists studied them. The rocks themselves were not mysterious, their true significance was. Why did so much iron accumulate during specific periods of Earth's history? Why do these deposits appear so prominently in ancient rocks while becoming far less common in younger ones? And why do they seem connected to a time when the planet operated differently from the Earth we know today? The deeper scientists investigated, the more difficult the questions became. Patterns emerged where none were expected. Certain chemical signatures appeared alongside the iron-rich layers. Distinct mineral structures suggested unusual conditions within ancient seas. Independent discoveries made in different parts of the world began pointing toward a remarkably similar conclusion. The oceans of that era may have contained extraordinary amounts of dissolved iron. Not small increases compared to modern conditions, but concentrations on a scale that is difficult to imagine today. This realization transformed the mystery. The iron deposits were no longer simply geological curiosities. They became evidence of an ancient environment unlike anything now existing on Earth. The rocks seemed to be describing oceans with a chemistry fundamentally different from modern seas. Yet this answer immediately created another puzzle. Modern oceans contain iron, but relatively little of it remains dissolved throughout the water. Something prevents it from accumulating in the enormous quantities suggested by the ancient record. So what was different billions of years ago? What allowed iron to spread through vast portions of Earth's oceans? Conditions made such an extraordinary world possible. The clues preserved inside mountains reveal that the oceans once behaved in ways that seem almost impossible today. They point toward a planet operating under unfamiliar rules, a planet whose seas carried immense quantities of dissolved iron across enormous distances. The rocks tell only part of the story. They reveal that the iron existed. They do not yet explain where it came from. To answer that question, the investigation must travel even deeper into Earth's past, to an age when the young planet itself looked far stranger than the red oceans it would eventually create. To understand how Earth's oceans may have become red, it is necessary to leave behind the familiar world entirely. Clues hidden in ancient rocks point toward a planet that no longer exists. Not another planet orbiting a distant star, but an earlier version of Earth itself. A world so different from the modern one that a visitor arriving there might struggle to recognize it as the same place. Continents were smaller. The atmosphere was different. The oceans followed unfamiliar rules. And beneath everything lay a restless planet still shaping its identity. Billions of years ago, Earth was a far more active world than the one humans know today. Volcanoes erupted across vast regions. Deep fractures opened within the crust. Molten material rose continually from the interior, carrying minerals and chemicals toward the surface. The young planet seemed almost unable to sit still. Every eruption altered the environment. Every geological upheaval added something new to the oceans. The process never truly stopped. Across the seafloor, hydrothermal systems released streams of mineral-rich water into the surrounding seas. Deep beneath the waves, Earth's interior continuously exchanged material with the ocean above. Iron flowed outward in enormous quantities. Other dissolved elements accompanied it, creating conditions unlike those found in modern seawater. Today, it is difficult to imagine such a world because modern oceans behave very differently. When iron enters present-day seawater, it rarely remains there for long. Chemical reactions remove much of it. The water most people see along coastlines or from satellites contains relatively small amounts of dissolved iron. Ancient Earth was operating under another set of conditions. The crucial difference was not the iron itself. What was missing? Modern air contains abundant oxygen. It surrounds every landscape, fills every breath, and influences countless chemical processes across the planet. Oxygen feels so ordinary it is easy to assume it has always been there. It has not. During much of Earth's early history, oxygen existed only in tiny amounts. The atmosphere lacked the invisible ingredient that modern life depends upon. The oceans reflected that reality. Without significant oxygen present, dissolved iron remained suspended within seawater rather than rapidly transforming into rust-like compounds. The iron accumulated. More arrived from volcanoes and hydrothermal systems. More continued entering from the planet's active interior. Over immense spans of time, the concentrations grew extraordinary. The result may have been oceans unlike any found today. Scientists cannot travel back to witness them directly, but the evidence suggests seas saturated with dissolved iron on a scale that modern environments rarely approach. The chemistry of those waters would have differed dramatically from present oceans. Appearance may have differed as well. This realization changes the way the mystery is viewed. Question is no longer why ancient oceans looked unusual. Real question becomes why modern oceans look the way they do. Blue oceans suddenly seem less inevitable. They are not a permanent feature of all planets. They are the product of very specific circumstances. Change the chemistry, alter the atmosphere, adjust a few critical ingredients, and an ocean may appear entirely different. The Earth of this distant era was not simply younger. It was stranger. Its skies carried different gases. Its oceans held different materials. Its landscapes experienced levels of geological activity rarely seen today. The entire planet functioned according to conditions that would feel unfamiliar to modern observers. Beneath all that strangeness, something unexpected was beginning to emerge. Life already existed, not forests, animals, not anything visible from a shoreline. The inhabitants of this ancient Earth were microscopic. Tiny organisms occupied oceans that stretched across the planet. Most would have gone unnoticed by any observer. They seemed insignificant compared to volcanoes, continents, and oceans. Yet appearances can be deceptive. While geology filled the seas with iron, another force was quietly developing within the water itself. It did not erupt from mountains. It did not rise from deep beneath the crust. It lived. And over time, it would begin changing the chemistry of the oceans, the composition of the atmosphere, and eventually the future of the planet. Transformation that ended the age of iron-rich seas was not driven by volcanic fire or geological upheaval. It came from life. More specifically, it came from organisms so small that billions could exist within a single drop of water. In the next chapter, those microscopic inhabitants begin rewriting Earth's story, one invisible change at a time. When people imagine forces capable of changing an entire planet, they usually think of dramatic events. They imagine colossal volcanoes darkening the sky. They picture asteroids striking the surface with unimaginable violence. They envision continents colliding, mountains rising, or oceans swallowing coastlines. These are the kinds of forces that seem worthy of planetary transformation. Its greatest revolution followed a very different path. It began in silence. Far beneath the notice of anything that would later walk, swim, or fly, countless microscopic organisms drifted through ancient seas. They possessed no intelligence, built no civilizations, and left behind no monuments. Most were so small that millions could gather within a space no larger than a grain of sand. Yet these tiny inhabitants would eventually alter the destiny of the world. The oceans they inhabited were unlike modern seas. Iron flowed through the water in extraordinary quantities. Oxygen remained scarce. The atmosphere above bore little resemblance to the air familiar today. To modern life, such conditions might appear hostile. To these ancient microbes, they were simply normal. This was the only world they had ever known. For immense stretches of time, life remained relatively simple. Microbial communities spread across shallow waters and deeper environments, surviving through a variety of chemical strategies. They gathered energy where they could find it, adapting to conditions that had persisted for hundreds of millions of years. Nothing about their existence suggested they were about to change the planet. If an observer could have watched Earth during this era, the world would have appeared remarkably stable. Oceans rose and fell, volcanoes erupted, continents shifted slowly across the globe. Life existed, but it seemed little more than a passenger carried along by geological forces far greater than itself. Then somewhere within those ancient seas, a new biological ability emerged. It did not arrive with fanfare. No visible signal announced its appearance. No dramatic transformation followed immediately. A small group of microbes discovered how to use sunlight in a way that would eventually reshape the Earth. Sunlight had always poured onto the planet's surface. Day after day, year after year, it crossed the oceans without changing the course of history. Now certain microorganisms began capturing that energy with increasing efficiency. They converted sunlight into usable fuel, allowing them to thrive in environments where light was abundant. The remarkable part was not the energy they gained. It was the waste they produced. As these microbes carried out their daily existence, they released tiny amounts of oxygen into the surrounding water. At first, the change was almost meaningless. The quantities were microscopic. The oceans were vast. Nothing visible happened. No shoreline altered its appearance. No mountain responded. The atmosphere remained largely unchanged. If anyone had been there to witness it, they would have noticed nothing at all. Yet history is filled with transformations that begin long before they become visible. Day after day, oxygen entered the water. Generation after generation, the process continued. Millions of years passed. The amounts remained small, but the production never truly stopped. This is one of the strangest lessons hidden within Earth's history. Planetary revolutions do not always begin with immense forces. Sometimes they begin with persistence. Tiny change repeated countless times can become more powerful than any single catastrophe. The microbes themselves had no intention of transforming the world. They were simply surviving. They did not know oceans would change. They did not know atmospheres would evolve. They could not imagine forests, animals, or humans. Yet each day they added another trace of oxygen to the sea. The accumulation was slow enough to escape notice, but steady enough to alter the future. And because the oceans already contained enormous quantities of dissolved iron, every molecule of oxygen entering the water was about to encounter something waiting for it. Consequences would become impossible to ignore. For the first time in Earth's history, oxygen and iron were beginning to meet within the same ocean. The first oxygen released by those ancient microbes did not rise into the atmosphere. It never had the chance. The moment oxygen entered the iron-rich waters of the ancient oceans, it encountered a world waiting to react. Hundreds of millions of years, dissolved iron had accumulated throughout the seas. It drifted through the water in quantities almost impossible to imagine today, carried there by volcanic activity, hydrothermal systems, and the restless interior of the young Earth. Now a new ingredient had arrived, and the encounter would change everything. At first the process was invisible. Tiny amounts of oxygen mixed with seawater and immediately found dissolved iron. The reaction happened naturally, requiring no guidance and no intention. Oxygen and iron were simply following the rules of chemistry. Yet what seemed like a minor interaction was quietly becoming one of the most important chain reactions in planetary history. Every molecule of oxygen removed a little iron from the water. Every generation of microbes produced more oxygen. Every year the balance shifted slightly. The changes were so gradual that no single moment marked the beginning of the transformation. There was no dramatic turning point, no instant when the oceans suddenly changed color. Instead, the process unfolded patiently across immense spans of time. The ancient seas were being altered one reaction at a time. As oxygen combined with dissolved iron, new compounds formed. Unlike the iron that had remained suspended within the water, these materials were heavier and less stable in solution. Slowly they began sinking toward the seafloor. The oceans were shedding their iron. Particle by particle, layer by layer, vast quantities of material settled through the water and accumulated below. Millions of years the deposits grew thicker. New layers formed above older ones. Process repeated so consistently that entire regions of the seafloor became covered with iron-rich sediments. The scale was extraordinary. These were not isolated patches scattered randomly across the planet. The deposits stretched across enormous areas. In some places, they eventually reached hundreds of meters in thickness. Long after the oceans that created them vanished, these layers would harden into stone and become part of the geological record. Today, many of those formations still exist. They stand within mountains, they appear in cliffs and exposed rock faces. They are mined as valuable sources of iron used in modern industry. Most people see them as mineral resources. Few realize they may represent the physical remains of an ancient environmental revolution. Connection is astonishing. Those iron-rich rocks are not merely deposits of metal. They are evidence that something fundamental changed within Earth's oceans. They record a time when dissolved iron was being removed from seawater on a massive scale. In a sense, they are the fossilized remains of a struggle between two planetary forces. On one side stood oceans saturated with iron. On the other stood microscopic life producing oxygen. Neither force was acting with purpose. Yet together they were reshaping the world. The more oxygen entered the water, the more iron disappeared. The more iron disappeared, the more the oceans changed. Gradually, the chemistry that had defined the ancient seas for countless ages began fading away. What had once seemed permanent was becoming temporary. The red ocean world was not simply evolving, being dismantled. This realization solves one mystery while creating another. Famous iron formations scattered across the planet are not random geological features. They may be records of oceans transforming before our eyes, if only we could travel back far enough to witness it. An even larger consequence was emerging. For a long time, oxygen remained trapped in this endless cycle, consumed almost as quickly as microbes produced it. The oceans absorbed it. The iron reacted with it. The seafloor collected the results. Slowly, something began to change. As more iron disappeared from the water, less oxygen was being used up. The first time, small amounts began surviving the journey. And once oxygen was no longer confined beneath the waves, its influence would spread far beyond the oceans themselves. It was about to reach the sky. For countless millions of years, the ancient oceans acted like a giant chemical trap. Oxygen entered the water day after day, produced by microscopic organisms drifting through sunlit seas. Yet almost none of it survived for long. Dissolved iron consumed it. Other reactive materials consumed it. The oceans seemed capable of absorbing every trace that life could create. The balance appeared stable, produced oxygen. The planet removed oxygen. The cycle continued. Stability in Earth's history often lasts only until a threshold is crossed. Slowly, almost imperceptibly, the chemistry of the oceans began changing. Vast quantities of dissolved iron had already been transformed and carried to the seafloor. Layer after layer of iron-rich sediment accumulated beneath the waves. The ancient sinks that had absorbed oxygen for so long were gradually losing their capacity to do so. No single moment marked the transition. No dramatic event announced its arrival. The world simply began behaving differently. For the first time, some oxygen remained after the reactions were finished. Tiny surplus appeared, then another, then another. What had once vanished almost instantly now lingered within the water. The oceans were no longer able to consume everything life produced. The balance that had defined an entire age of Earth was shifting. The consequences would reach far beyond the sea. As oxygen accumulated, increasing amounts escaped into the atmosphere. At first, the quantities remained small. The air above the planet still looked nothing like modern skies. Yet the direction of change had become impossible to reverse. Earth was entering a new chapter. The transformation unfolded so gradually that no observer living through it could have appreciated its scale. Millions of years passed. Oceans continued changing. Atmospheric chemistry evolved. The familiar conditions of the red ocean world slowly faded into history. What makes this moment so remarkable is that the planet was not merely experiencing a chemical adjustment. It was undergoing a complete environmental revolution. The oceans that had once carried extraordinary amounts of dissolved iron were becoming different places. The atmosphere that had existed for ages was beginning to change composition. Interactions between land, sea, air, and life were being rewritten. The world was becoming less familiar to its oldest inhabitants, and more suitable for forms of life that did not yet exist. This is one of the great paradoxes of Earth's story. The rise of oxygen eventually made complex life possible. Every animal, every forest, every ecosystem visible today depends upon conditions that emerged from this transformation. Even the existence of humans traces back to these ancient changes. From a modern perspective, oxygen appears to be a gift. For many organisms living at the time, it may have seemed more like a threat. Most early life evolved in environments where oxygen was scarce or absent. Their biological systems were adapted to a different world. The increasing presence of oxygen introduced a powerful new chemical force into ecosystems that had never experienced it before. benefited some organisms, created problems for others. Habitats changed. Chemical conditions shifted. Ancient communities faced pressures unlike anything they had encountered in the past. The same process that opened doors for future life may have closed doors for countless existing species. In that sense, the rise of oxygen was both a beginning and an ending. It marked the decline of the red ocean era, prepared the way for future biological complexity, and it may also have triggered one of the earliest environmental crises the planet had ever known. The irony is difficult to ignore. The substance that would eventually allow humans to breathe, think, and exist may have been deeply destructive when it first appeared in abundance. What seems beneficial from one perspective can appear catastrophic from another. It was not becoming universally better. It was becoming different. The red ocean world had dominated the planet for immense stretches of time. Now it was disappearing. In its place emerged a new Earth, shaped increasingly by oxygen and the consequences that followed. The transition was far from peaceful. For many ancient organisms, survival itself had become uncertain. And that raises a question that still echoes across billions of years. If oxygen transformed the planet so dramatically, how did life endure the crisis it created? Today, oxygen feels so essential that it is difficult to imagine life without it. Every breath depends upon it. Every forest produces it, every animal requires it. The presence of oxygen seems so natural that many people assume it has always been a welcome part of Earth's environment. Reality is far stranger. There was a time when oxygen was not a gift, it was a threat. For most of Earth's early history, life evolved in a world where oxygen was nearly absent. Entire ecosystems developed under conditions that modern organisms would find unfamiliar. Generation after generation adapted to environments shaped by different chemical rules. These ancient forms of life did not need oxygen to survive because oxygen was not part of the world they knew. For them, the rise of oxygen represented something new. And new does not always mean beneficial. Oxygen is highly reactive. Quality makes it valuable for complex life today, but it also makes it potentially dangerous. In the wrong environment, oxygen can disrupt delicate biological processes and damage cells that evolved without protection against it. To many ancient organisms, oxygen may have been less like nourishment and more like poison, yet the oxygen-producing microbes continued their work. Day after day, they captured sunlight and released oxygen into the environment. It began as a tiny biological innovation was becoming a planetary force. The oceans absorbed increasing amounts. The atmosphere slowly accumulated more. The concentration remained low compared to modern levels, but the direction of change was unmistakable. The world was becoming more oxygen-rich. At first, the effects were localized. Certain regions experienced subtle chemical shifts. Some microbial communities adapted successfully. Others retreated into environments where oxygen remained scarce. The changes unfolded gradually enough that life had opportunities to respond. But Earth was not standing still. Millions of years passed. Then tens of millions. The accumulation continued. Eventually, oxygen levels rose beyond what many ancient ecosystems could comfortably tolerate. What had once been a minor environmental factor became a growing challenge. Organisms that had thrived for vast stretches of time suddenly found themselves living in a world that no longer favored their way of life. The transformation was unlike anything that had happened before. Not because it arrived suddenly, but because it arrived everywhere. Most environmental disasters in Earth's history are associated with dramatic events. Volcanic eruption darkens the sky. An asteroid strikes the surface, a continent shifts position. These events attract attention because they are violent and obvious. The oxygen crisis followed a different pattern. There was no explosion, no impact, no visible catastrophe. An invisible gas was quietly changing the rules of survival across the entire planet. Ancient microbial populations likely declined. Some groups may have disappeared entirely. Ecological relationships that had existed for immense periods of time were disrupted. Communities built under one set of conditions found themselves facing another. The most remarkable aspect of the crisis was its source. The disaster was not imposed from outside. Life itself created it. The very organisms producing oxygen were not attempting to transform the world. They were simply surviving. Yet their collective activity altered the environment so profoundly that other forms of life struggled to cope with the consequences. It was an unintended revolution. A biological success story for some organisms became a crisis for others. Viewed from a modern perspective, the rise of oxygen appears necessary because it eventually led to the world humans inhabit. Viewed from the perspective of countless ancient microbes, however, the same event may have looked entirely different. It may have felt like the end of their world. This possibility leads to one of the most surprising ideas in Earth's history. The first known global environmental disaster may not have been caused by volcanic fire, shifting continents, or objects falling from space. It may have been caused by life. Tiny microorganisms, invisible to the naked eye, unintentionally transformed the chemistry of oceans, altered the atmosphere, and changed the future of every living thing that followed. Yet the story was only beginning. As oxygen continued spreading, its influence reached beyond biology. The atmosphere itself was changing, and those changes were preparing the planet for another transformation. One that would affect the climate of the entire Earth. Transformation that began beneath the waves did not remain there. Millions of years, the story of oxygen seemed tied primarily to the oceans. Iron-rich waters reacted with it. Ancient ecosystems struggled to adapt to it. The chemistry of the seas slowly shifted because of it. Yet the oceans were only one part of a much larger system. Above them stretched the atmosphere, and the atmosphere was changing too. To understand what happened next, it is necessary to imagine a sky unlike the one visible today. The modern atmosphere feels familiar because every human who has ever lived has known roughly the same air. Yet during the age of red oceans, the atmosphere followed different rules. One of its most important ingredients was methane. Today, methane exists only in relatively small quantities compared to other gases. In the distant past, however, it likely played a far more significant role. The young sun produced less energy than it does now, meaning Earth received less warmth from space. Under those conditions, maintaining liquid oceans should have been difficult. Yet the oceans remained. Planets stayed warm enough to support water and life. Methane was one reason why. Acting as a powerful greenhouse gas, methane helped trap heat within the atmosphere. It functioned like a protective blanket surrounding the young Earth, preserving temperatures that allowed oceans to remain liquid despite a dimmer sun overhead. Immense spans of time, this arrangement appeared stable. The oceans existed, the atmosphere retained warmth, endured. Then oxygen began rising. At first the effects seemed minor. Oxygen concentrations remained relatively low, and methane continued playing its familiar role. Chemistry has little regard for stability. When oxygen and methane coexist, they do not simply ignore one another. They react. Slowly but persistently, oxygen began removing methane from the atmosphere. The process unfolded so gradually that no observer could have recognized its significance in real time. Millions of years passed as tiny amounts of methane disappeared. The atmosphere continued functioning. The climate remained recognizable. Nothing appeared dramatically different. Yet the balance was shifting. Protective blanket surrounding Earth was becoming thinner. As methane concentrations declined, the atmosphere lost some of its ability to retain heat. The change was not immediate. Planetary systems rarely respond instantly. Instead, Earth reacted the way enormous systems often do. Slowly at first, then increasingly noticeably, temperatures began to respond. The atmosphere itself was being rearranged. This realization reveals one of the most fascinating aspects of Earth's history. The oxygen revolution was never confined to a single environment. Oceans, atmosphere, climate, and life were connected parts of the same system. Change in one area inevitably produced consequences elsewhere. The microbes producing oxygen beneath the waves were influencing the sky above them. The sky, in turn, was influencing the climate. The climate would soon influence the entire planet. One transformation was triggering another. Like a series of falling dominoes, each change increased the likelihood of the next. Scientists studying ancient rocks have uncovered clues suggesting that major climate shifts may have occurred during this period. Geological evidence points toward environmental changes difficult to explain without significant alterations to atmospheric chemistry. Timing is intriguing. As oxygen rose and methane declined, the planet appears to have entered an increasingly unstable phase. The connection is difficult to ignore. The same biological process that cleared dissolved iron from ancient oceans may also have altered Earth's climate. What began as a microscopic innovation was becoming a planetary chain reaction. The oceans changed. The atmosphere changed. Now the climate was beginning to change as well. And climate has a way of amplifying transformations that might otherwise remain small. By the time the consequences became fully visible, the planet was already moving towards something extraordinary. Oxygen continued rising. Methane continued falling. Temperatures continued shifting. The balance that had sustained Earth for ages was weakening. Ahead lay one of the most remarkable possibilities in planetary history, a period when ice may have spread across the globe so extensively that Earth itself began to resemble a frozen world. Cooling did not stop. As methane declined and Earth's atmosphere lost part of its ability to trap heat, the consequences began spreading across the planet. Temperatures fell gradually at first, almost imperceptibly. Yet climate systems are rarely simple. A small change can trigger another, which triggers another still, until the world begins moving in a direction that becomes increasingly difficult to reverse. Maybe exactly what happened. Ice started expanding. Regions that had once remained free of permanent freezing began accumulating more snow and ice than they lost each year. White surfaces spread across larger areas of the planet. On the surface, this might not seem particularly significant. Ice possesses a remarkable property that can transform climates. It reflects sunlight. Oceans absorb solar energy. Ice sends much of that energy back into space. As frozen regions expanded, Earth absorbed less warmth. The planet cooled further. Additional ice formed. More sunlight was reflected away. The cycle reinforced itself. Cooling created ice. Ice created more cooling. Process continued. Over immense spans of time, Earth may have approached one of the most extraordinary states in its entire history. Frozen world. Geological evidence discovered across multiple continents suggests that ancient glaciers reached regions far closer to the equator than scientists once believed possible. Rocks bearing signs of glacial activity appear in places that should have been relatively warm. The evidence has puzzled researchers for decades because it points toward a climate unlike anything found on modern Earth. Some scientists proposed a startling explanation. Perhaps the planet became almost entirely frozen. According to this idea, often called snowball Earth, ice spread across oceans and continents on a near-global scale. Frozen surfaces stretched from pole to pole. Much of the planet's water may have existed beneath thick layers of ice. Viewed from space, would have appeared more white than blue. It is a breathtaking image. A world once defined by iron-rich oceans transformed into a frozen sphere drifting through darkness. Yet not all researchers agree. Some argue for a less extreme scenario. Rather than complete global freezing, they envision a slush-ball Earth. In this interpretation, extensive ice covered enormous regions, but areas of open water persisted near the equator. Climate was severe, yet not entirely frozen. The debate continues today, and perhaps that uncertainty makes the story even more fascinating. The rocks reveal that something extraordinary happened. The exact details remain a subject of investigation. Like so many mysteries from deep time, Earth preserved enough evidence to raise profound questions while withholding complete certainty. Makes the possibility especially remarkable is its connection to the oxygen revolution. The same biological innovation that gradually transformed the oceans may have contributed indirectly to one of the most dramatic climate crises in planetary history. Microbes producing oxygen helped remove methane. The atmosphere changed. Temperatures declined. Ice expanded. Chain reaction unfolded across the world. The rise of oxygen was not simply a triumph leading directly toward complex life. It may also have plunged the planet into environmental chaos. The irony is difficult to overlook. Process that would eventually support forests, animals and humans may first have helped create one of Earth's harshest environments. Yet life did not disappear. That fact may be the greatest mystery of all. Earth became a complete snowball or a partially frozen slush ball. Survival appears almost miraculous. Beneath expanding ice, within isolated pockets of water, around volcanic regions, or near hydrothermal systems, hidden in the darkness of the deep ocean, life endured. Somewhere ecosystems persisted. Somewhere microscopic communities continued adapting to conditions that seemed impossible. The frozen world did not mark the end of life's story. Instead, it became one of its most remarkable tests. As ice advanced across the planet and ancient environments vanished beneath frozen surfaces, living organisms faced challenges unlike any they had encountered before. The question was no longer whether life could transform the world. The question had become far more urgent. How did life survive a world that may have nearly frozen solid? Frozen world should have been the end. That is what makes the mystery so compelling. If ice truly spread across enormous portions of the planet, If temperatures fell to levels unseen in earlier ages, if oceans vanished beneath expanding frozen surfaces, then life should have faced one of the greatest survival challenges in Earth's history. Entire environments disappeared, familiar ecosystems collapsed. Conditions that had once supported thriving communities were transformed beyond recognition. Yet life endured. Somehow, despite everything, the story continued. The evidence is impossible to ignore. Life existed before the great freezing episodes, and life existed afterward. Between those two facts lies one of the most fascinating questions in evolutionary history. Where did it survive? Scientists searching for answers often begin by examining places that seem almost otherworldly today. Hidden throughout the modern planet are environments where life thrives under conditions that appear hostile or even impossible. These locations offer glimpses into what survival may have looked like during Earth's darkest ages. Far beneath the ocean's surface, hydrothermal vents release heat from the planet's interior. Around these underwater oases, entire communities flourish without relying directly on sunlight. Energy comes from chemistry rather than daylight. Life persists in darkness that has lasted for millions of years. These environments provide an intriguing clue. Some ancient organisms survived in similar refuges while ice dominated the surface world. Other possibilities exist as well. Volcanic regions may have maintained pockets of warmth. Areas of thinner ice could have allowed limited sunlight to reach the water below. Seasonal melting may have created temporary habitats where microbial communities continued functioning. Deep beneath frozen surfaces, liquid water may have remained protected from the worst conditions above. The image that emerges is not necessarily one of a planet completely devoid of life. Instead, Earth begins to resemble a patchwork of hidden sanctuaries. Scattered across a hostile world, small regions remained habitable. Small regions became lifelines. Within those isolated environments, life retreated, adapted, and waited. The remarkable aspect of this story is not merely survival, it is persistence. Life repeatedly demonstrates a refusal to disappear, even when circumstances seem overwhelmingly unfavorable. Throughout Earth's history, environmental crises have reshaped ecosystems countless times. Again and again, living organisms find ways to endure. Sometimes survival occurs in places no one would expect. Sometimes the most important chapters unfold far from the surface. The deeper scientists investigate extreme environments, the more surprising discoveries they make. Microbial communities inhabit boiling waters, frozen deserts, acidic pools, and deep underground ecosystems. Life appears capable of occupying niches once considered impossible. This realization changes how the frozen world is viewed. Instead of imagining a dead planet, researchers increasingly imagine hidden worlds concealed within the larger catastrophe. Small populations persist, communities adapt to new conditions, evolution continues its work in silence. Evolution never truly stops. Even during crises, even during planetary upheavals, natural selection continues operating wherever life survives. Organisms better suited to changing conditions gain advantages. New adaptations emerge. Different strategies are tested. Appears from a distance to be a period of stagnation may actually become a period of experimentation. Some scientists suspect that environmental stress itself may have encouraged important evolutionary innovations. Harsh conditions create powerful pressures. Survival demands flexibility. Organisms capable of adapting gain opportunities unavailable during more stable times. The idea is profound. Some of life's greatest breakthroughs may not have occurred during periods of comfort. They may have emerged during periods of struggle. Frozen world, rather than halting evolution, may have redirected it. This theme appears repeatedly throughout Earth's story. Catastrophes reshape environments. Life responds. New possibilities emerge from unexpected circumstances. The pathway forward is rarely obvious, yet somehow it continues. Beneath the ice, within isolated refuges, hidden from view, life was doing more than surviving. It was changing, and those changes eventually influenced the future of the planet in ways that no organism drifting through those ancient waters could possibly have imagined. Survival is only the beginning of a story. A world can endure a crisis and remain unchanged, but life rarely follows that pattern. Once organisms survive an environmental upheaval, a second process begins. They adapt, they experiment, they discover new ways of existing within a transformed world. That is what may have happened during Earth's long recovery from its frozen ages. The planet was changing. Oceans behaved differently. Atmospheric chemistry continued evolving. Habitats appeared and disappeared. Conditions that had remained stable for immense periods were suddenly less predictable. In such an environment, flexibility became valuable. Traits that once seemed unimportant gained significance. Abilities that offered only minor advantages suddenly mattered. The rules of survival shifted. Throughout Earth's history, environmental pressure has acted like a filter. Organisms unable to adapt often struggle. Capable of responding to new challenges gain opportunities. Time, these pressures can produce remarkable changes. The frozen world may have provided exactly that kind of pressure. Within isolated refuges, microbial communities encountered new circumstances. Resources varied, temperatures fluctuated. Different populations became separated from one another. Each group faced its own challenges and developed its own solutions. Evolution responded, not with a grand plan, not with a predetermined destination, but with countless small adjustments accumulating over time. Some organisms developed ways to use available resources more efficiently. Others discovered new metabolic strategies that allowed survival under unusual conditions. Relationships formed between species that depended upon one another. Cooperation became increasingly important in certain environments. Life was becoming more versatile. The changes were subtle at first. No dramatic new creatures appeared. The world was still dominated by microscopic life. Yet beneath that apparent simplicity, important developments were unfolding. Organisms were learning to occupy environments that would once have been difficult or impossible. The web of life was becoming more interconnected. This is one of the most fascinating aspects of evolution. It rarely moves in a straight line. Progress is not a ladder with clearly defined steps. Instead, evolution resembles an intricate network of experiments. Some pathways fail, others succeed. Environmental conditions determine which adaptations prove useful and which disappear. Frozen ages may have increased the number of experiments taking place. Every challenge encouraged innovation. Every changing condition rewarded flexibility. Every surviving population contributed to the ongoing story. Appears from a distance to be a period of hardship may actually represent a period of creativity. Scientists studying ancient life increasingly suspect that some of the foundations for future biological complexity emerged during these turbulent eras. The evidence remains incomplete, as deep-time mysteries often are, but intriguing patterns continue to appear. Certain innovations seem to emerge around periods of environmental instability rather than during long stretches of calm. The implication is remarkable. Conditions that look destructive on the surface may sometimes create opportunities hidden beneath the chaos. Environmental crises remove old constraints. They force adaptation. They encourage new solutions. While many organisms struggle, others discover possibilities that did not exist before. Life learns new tricks because it must. The frozen world may have been one of evolution's greatest classrooms. The organisms drifting through those ancient oceans could not know they were participating in changes that would echo across billions of years. They were simply responding to immediate challenges. Yet the cumulative result of countless adaptations was gradually transforming the biological landscape of the planet. Fertility increased, relationships deepened, possibilities expanded. The Earth emerging from these difficult periods was not identical to the one that entered them. Life had changed, and it would continue changing. Far beyond the awareness of any microorganism, the planet was moving toward a threshold unlike anything it had experienced before. The innovations accumulating through countless generations were preparing the way for a future transformation so profound that it would alter the course of life's history forever. The signs remained subtle, the destination remained hidden, but the foundations were already being laid. Somewhere beyond the horizon of deep time, a new chapter was waiting to begin. The ice did not retreat all at once. It rarely changes that way. The frozen ages that had reshaped the planet unfolded across immense stretches of time, and their ending followed the same pattern. Gradually, almost imperceptibly at first, conditions began shifting. Temperatures stabilized. Ice sheets withdrew from some regions. Oceans reclaimed spaces that had remained frozen for ages. The transformation was slow enough that no living organism could have witnessed its full extent. Millions of years passed, then millions more. Yet beneath that slow progression, something profound was happening. The Earth emerging from its harshest conditions was becoming increasingly recognizable. Not recognizable in the sense that a modern observer would feel at home there, but recognizable as a world moving toward the future rather than away from it. The atmosphere continued evolving, the oceans continued changing, life continued adapting. Planet was finding a new balance. One of the most important factors remained oxygen. What began as a biological byproduct released by microscopic organisms had become a force influencing nearly every aspect of Earth's development. Long ago, oxygen transformed iron-rich oceans. Later, it altered the atmosphere and contributed to dramatic climate shifts. Now its influence extended even further. It was helping shape the possibilities available to life itself. The significance of this change is difficult to overstate. Billions of years, Earth had been dominated by microscopic organisms. They filled the oceans. They transformed environments. They survived planetary crises. Yet despite their success, life remained relatively simple in structure. Planets' ecosystems were complex, but the organisms themselves were generally composed of single cells. Pattern had persisted for an astonishing length of time. Then, the subtle signs of something different began appearing. The exact sequence remains one of the great mysteries of evolutionary history. But scientists believe the changing conditions of the planet created opportunities that had not existed before. Rising oxygen levels may have played an especially important role. More oxygen meant more available energy. More energy allowed biological systems to attempt increasingly ambitious forms of organization. Possibilities expanded. At first, the changes were modest. Cells interacted more closely. Communities became more interconnected. Biological relationships grew increasingly sophisticated. Then gradually a remarkable idea began taking shape. What if individual cells did not have to live entirely alone? What if cooperation offered advantages that isolation could not? The concept seems simple from a modern perspective because every animal, plant, and human body depends upon it. Yet at the time, it represented a revolutionary possibility. Separate cells could work together. Different cells could perform specialized tasks. Collections of cells could function as a unified organism. The implications were enormous. For the first time, Earth may have been approaching the threshold of multicellular life. The transition did not happen overnight. Evolution never moves with such speed. Countless experiments likely failed, persisted. Over vast periods of time, increasingly complex forms of cooperation emerged. Foundations of a new biological world were being assembled piece by piece. The irony is extraordinary. The story began with red oceans filled with dissolved iron. Tiny microbes altered those oceans by producing oxygen. Oxygen transformed the atmosphere. Atmospheric changes influenced climate. Climatic upheavals challenged life. Adapted. New opportunities emerged. One transformation led to another. Each chapter created the conditions for the next. What once appeared to be disconnected events now reveal themselves as part of a single unfolding narrative. Red Ocean World was not merely disappearing. It was giving birth to something new. The Earth that emerged from these ancient transformations contained greater biological potential than any previous version of the planet. The ingredients for complexity were accumulating. The stage was being prepared for developments that would eventually fill the oceans with unfamiliar creatures and reshape ecosystems across the globe. After billions of years dominated by microscopic life, the world was approaching a biological revolution. First hints had already appeared. Soon, those hints would become impossible to ignore. And when they did, life would begin one of the most remarkable expansions in the history of the Earth. It is tempting to think of the red oceans as a lost world, a strange chapter buried so deeply in the past that it has little connection to the present. Billions of years separate that era from modern civilization. Entire continents have shifted. Countless species have appeared and vanished. The planet itself has changed beyond recognition. Every ordinary measure, the red ocean world is gone, and yet it is not. Its influence remains everywhere. The remarkable truth is that ancient oceans did not simply disappear without leaving a trace. Their legacy became woven into the fabric of the modern Earth. What happened beneath those iron-rich waters continues to shape landscapes, ecosystems, industries, and even the air flowing through human lungs. Past is closer than it appears. Across the world, mountain ranges contain evidence of events that began during the age of red oceans. Layers of iron-rich rock rise from the ground in places separated by entire continents. These formations often appear ordinary to anyone passing by. Yet hidden within them is a record of one of the greatest environmental transformations in planetary history. Rocks are ancient. The story they tell is even older. Long before animals existed, long before forests spread across the land, vast quantities of dissolved iron settled from prehistoric oceans and accumulated on the seafloor. Over immense stretches of time, those sediments hardened into stone. Geological forces later lifted them upward, exposing them to the surface world. Today they remain visible. In some regions they form dramatic cliffs and mountains. In others they lie beneath cities, roads, and fields. Most people never realize what they are looking at. Yet these formations became some of humanity's most valuable geological resources. The iron extracted from them has helped build civilizations. It exists in bridges crossing rivers. It exists in railways stretching across continents. It exists in skyscrapers rising above modern cities. The metal supporting much of the modern world may trace its origins to transformations that occurred billions of years before complex life appeared. Realization creates an unexpected connection between deep time and everyday life. The inheritance of the red oceans is not confined to museums or scientific papers. It surrounds us. The steel in buildings, vehicles, machinery, and infrastructure often began its journey in ancient seas that no longer exist. Every piece of iron carries a history reaching back toward a world of dissolved minerals, oxygen-producing microbes, and changing planetary chemistry. The influence of those ancient oceans extends even further. The oxygen revolution that transformed iron-rich waters also reshaped the atmosphere. Process unfolded gradually across unimaginable spans of time, yet its consequences remain present every moment of every day. Modern life depends upon conditions that emerged because ancient microorganisms altered the chemistry of their world. Every breath carries part of that inheritance. The connection is easy to overlook because oxygen feels ordinary. It surrounds us constantly. Yet the atmosphere humans depend upon is not the atmosphere Earth originally possessed. It is the product of a transformation that began within ancient oceans long before animals existed. In a sense, the red ocean era helped create the modern sky. What initially appears to be an obscure geological mystery becomes something deeply personal. The story is no longer only about vanished oceans. It becomes a story about why the world looks the way it does today, why the atmosphere contains oxygen, why iron deposits exist, why Earth's chemistry differs so dramatically from its earliest state. Further the investigation progresses, the clearer the connection becomes. The red ocean world was not merely an ancient chapter that ended. It became the foundation upon which later chapters were built. Its influence survived every geological upheaval, every climate crisis, and every evolutionary transition that followed. And that leads to an even larger question. If the transformations that began in those ancient seas helped shape the modern planet, could they also have helped create the conditions necessary for complex life itself? The answer may reveal why humanity's existence is connected to red oceans more deeply than anyone once imagined. Few questions in science are more profound than this one. Why did complex life appear when it did? Billions of years, Earth was inhabited almost entirely by microscopic organisms. Life existed, it adapted, transformed the planet. Yet despite all that success, the world remained largely invisible to the naked eye. Oceans were filled with living communities, but there were no animals swimming through the water, no forests stretching across landscapes, and no creatures capable of observing the world around them. Then something changed. The transition did not happen suddenly, and it certainly did not happen for a single reason. Evolution is rarely that simple, yet many scientists increasingly believe that one factor played a crucial role in opening the door to greater biological complexity. Factor was oxygen. The idea begins with a simple observation. Complexity requires energy. A single microscopic cell can survive with relatively modest resources. A larger organism faces entirely different demands. Specialized tissues require energy. Movement requires energy. Communication, repair, and reproduction all require energy. The more complicated an organism becomes, the greater its energy needs. This creates a challenge. Without access to sufficient energy, complexity remains limited. For much of Earth's early history, those limits were difficult to overcome. Persisted, but biological possibilities remained constrained. Then the oxygen revolution began reshaping the planet. The chain of events stretched across unimaginable spans of time. Microscopic organisms evolved the ability to release oxygen. Oxygen reacted with dissolved iron. Iron-rich oceans gradually changed. The atmosphere slowly accumulated oxygen. Climate shifted. Ecosystems adapted. Each step built upon the previous one. No single event created complex life. Instead, countless transformations worked together. preparing the planet over billions of years. The result was a world increasingly capable of supporting larger and more sophisticated forms of biology. Oxygen provided opportunities that earlier ecosystems could not easily offer. Organisms capable of utilizing it gained access to greater amounts of energy. Over immense periods, this additional energy expanded what evolution could accomplish. The implications were extraordinary. Cells could cooperate more effectively. Biological systems could become more specialized. Organisms could grow larger and more complex. Possibilities multiplied. Viewed from this perspective, the rise of oxygen was not merely an environmental transformation. It was an expansion of evolutionary potential. Entire categories of life that would eventually emerge depended upon conditions that earlier Earth simply could not provide. This realization creates a remarkable connection between ancient oceans and the modern world. The Red Ocean era often appears distant and abstract. It belongs to a time before animals, before plants, before anything recognizable. Yet the chain of events that began in those strange iron-rich waters may have influenced every complex organism that followed, including us. The thought is difficult to ignore. Without iron-rich oceans, the oxygen revolution might have unfolded differently. Without the oxygen revolution, atmospheric conditions might have remained fundamentally altered. Without those atmospheric changes, the opportunities that supported increasing biological complexity may never have emerged in the same way. Path leading toward animals, ecosystems, and eventually humans could have looked entirely different. Perhaps it would never have existed at all. Of course, Earth's history is filled with uncertainty. Scientists continue debating details and exploring alternative possibilities. Yet the broader connection remains compelling. The world humans inhabit today may owe more to those ancient red oceans than anyone once suspected. The oceans themselves vanished long ago. Their influence did not. In a sense, the strange seas of Earth's distant past helped prepare the stage upon which all later life would appear. What seemed like a forgotten geological curiosity now reveals itself as a pivotal chapter in the story of existence itself. And once that possibility is considered, the mystery expands far beyond Earth. If ancient red oceans helped create the conditions for complex life here, could similar worlds exist elsewhere in the universe, following comparable paths toward their own unknown futures? For most of human history, the story of Earth seemed unique. The oceans, the atmosphere, the continents, and the living world appeared to belong exclusively to this planet. Ancient red oceans, if they existed, might seem like a strange detail buried within Earth's private history, interesting perhaps, but disconnected from anything beyond our world. Modern astronomy has changed that perspective. Today, scientists know that planets are not rare. They are everywhere. Thousands have already been discovered orbiting distant stars. Many more likely remain hidden beyond the limits of current technology. Some are larger than Earth, others are smaller. Some circle stars unlike the Sun, others travel around suns that appear remarkably familiar. Each world carries its own history. Each world may possess environments that challenge human expectations. And that is where the story of red oceans becomes unexpectedly important. Researchers studying Earth's distant past are not simply investigating ancient geology. They are also building a guide for understanding worlds that may exist far beyond our solar system. The more scientists learn about how dramatically Earth changed through time, the more cautious they become about assuming that habitable planets must resemble the modern Earth. Our world was once profoundly different, yet life still found a way to exist. That lesson matters. When astronomers search distant planets, they cannot visit them directly. Most appear only as tiny points of light. Scientists must rely on subtle clues gathered from immense distances. They study atmospheres, estimate temperatures, and search for signs that liquid water might exist. The challenge is determining what those worlds actually look like. And Earth's history provides a valuable reminder. Habitability may wear many faces. Modern oceans appear blue because of the specific chemistry that exists today. Change the chemistry, and the appearance can change as well. Ancient red oceans demonstrate that a planet capable of supporting life does not necessarily need to resemble the Earth visible from modern satellites. An ocean might be red, or green, or dark enough to appear almost black. Under different environmental conditions, entirely unfamiliar colors could emerge. The idea feels strange because humans instinctively treat modern Earth as the standard model for life-bearing worlds. Earth itself spent billions of years failing to match that model. planet was habitable long before it became familiar. This realization opens remarkable possibilities. Some distant worlds may currently resemble stages of Earth's past rather than its present. A planet with iron-rich oceans and limited oxygen could appear alien to modern observers while still supporting microbial ecosystems. Another world might be undergoing its own oxygen revolution. Yet another could exist somewhere between those stages, following a path unlike anything found in our solar system. The universe may contain countless variations. Scientists increasingly recognize that understanding Earth's history expands the range of environments they are willing to consider. Instead of searching only for planets that look like modern Earth, they can search for planets that resemble ancient Earth as well. That subtle shift dramatically increases the possibilities. The most fascinating implication arrives near the end of the investigation. What if Earth's red oceans were not unusual at all? What if they represent a common stage in the evolution of living worlds? Perhaps countless planets begin with environments dominated by dissolved minerals and unfamiliar atmospheric chemistry. Perhaps microbial life alters those environments over time. Perhaps oceans change color as biological and geological processes interact. The exact details would vary from world to world. The underlying pattern might not. If that possibility is correct, then Earth's most alien past may actually be one of the most useful tools humanity possesses for recognizing life elsewhere. The strange red oceans that once covered portions of our world become more than an ancient mystery. They become a lesson, a reminder that living planets are capable of extraordinary transformations, and a reminder that when humanity eventually discovers another inhabited world, it may not resemble the Earth of today. It may resemble the Earth that existed billions of years ago. Yet even as scientists look outward toward distant planets, another challenge remains much closer to home. The deeper they investigate Earth's earliest history, the more they discover how much of that history has been lost. The deeper scientists travel into Earth's past, the stranger the investigation becomes, because the evidence grows clearer, because it disappears. This creates one of the most frustrating mysteries in all of science. The era of red oceans may have been one of the most important chapters in planetary history. It influenced the atmosphere, reshaped the oceans, transformed ecosystems, and helped prepare the conditions for complex life. Despite its significance, direct evidence remains surprisingly scarce. The reason is both simple and unsettling. Earth is remarkably good at destroying its own history. Unlike the Moon, which preserves ancient scars across its surface for billions of years, Earth rarely leaves anything untouched for long. The Moon is a museum, Earth is a construction site. Everything moves, everything changes, everything is eventually recycled. Mountains rise from the ground only to be worn away by wind, water, and ice. Rivers carry fragments of ancient landscapes toward the sea. Continents drift across the globe at a pace too slow for human perception, yet powerful enough to reshape the planet entirely. Oceans open, expand, and eventually disappear. Even the crust beneath our feet is not permanent. It is constantly being renewed. This process has been operating for billions of years. Entire sections of Earth's surface have vanished into the interior through plate tectonics. Ancient seafloors have been consumed. Geological records have been folded, melted, fractured, and transformed. Landscapes that once existed on a global scale can disappear so completely that almost no trace remains. Consequences are astonishing. Imagine attempting to reconstruct the history of an entire civilization after nearly all of its cities, books, monuments, and artifacts had been destroyed. Now imagine that the destruction continued for billions of years. That is the challenge scientists face. The Earth that existed during the era of red oceans is gone. Not hidden, gone. What remains are fragments. Small pieces that somehow escaped destruction while countless others vanished forever. This reality transforms geology into something resembling detective work. Researchers are not examining a complete record. They are assembling a story from scattered clues preserved by extraordinary luck. A single rock formation may contain information that survived billions of years of planetary recycling. A mineral buried deep within ancient crust may preserve evidence of environments that no longer exist. Entire scientific investigations sometimes begin with discoveries made in remote regions where pieces of Earth's oldest history remained untouched by processes that erased similar records elsewhere. The search takes scientists to some of the most isolated places on the planet: ancient cratons, remote deserts, weathered mountain ranges, exposed rock formations standing far from modern cities. These locations may appear unremarkable to most observers, yet they contain some of the oldest surviving witnesses to Earth's distant past. Every surviving fragment matters. Every preserved layer becomes valuable. Every clue helps fill gaps within a story that has been partially erased. The deeper researchers look, the more remarkable the situation becomes. Some estimates suggest that more than half of Earth's earliest geological history may be permanently lost. Entire chapters vanished before scientists ever had an opportunity to read them. Possibility changes the way the evidence is viewed. The mystery is not simply what happened during the age of red oceans. The mystery is how much of that story disappeared forever. What environments existed that left no surviving trace? Transitions occurred that can no longer be reconstructed. What clues were destroyed long before humanity evolved to search for them? Questions are impossible to answer completely. Yet that uncertainty makes every surviving fragment even more precious. Scientists are attempting to reconstruct an ancient world using only the remnants that escaped a planetary recycling machine operating for billions of years. It is an extraordinary challenge, and it leads to an equally extraordinary realization. If so much of Earth's history has vanished, then even the smallest surviving clues may contain information far beyond what anyone once imagined. The next step in the investigation reveals how researchers extract entire worlds from fragments so tiny that they can fit within the palm of a hand. If Earth's earliest history has been largely erased, how can scientists know anything about it at all? The answer lies within some of the smallest survivors of deep time: mountains, not continents. Vast geological formations visible from space. Most valuable witnesses are often tiny crystals hidden inside ancient rocks. Some are no larger than grains of sand, yet within them exist information capable of spanning billions of years. At first glance, such a claim seems impossible. A crystal appears lifeless and simple. It does not write records. It does not preserve photographs. It cannot intentionally communicate with the future. And yet, when these minerals formed, they captured subtle details about the environments surrounding them. Details remain locked inside, waiting. Scientists sometimes describe certain ancient minerals as time capsules, and the comparison is remarkably accurate. During their formation, atoms became arranged in specific patterns. Tiny chemical traces were trapped within crystal structures. Variations in temperature, water chemistry, atmospheric conditions, and geological activity left signatures so subtle that no human could notice them without specialized tools. Yet they survived. Billions of years passed. Continents drifted, mountains rose and eroded, oceans opened and closed. Still, some of these microscopic witnesses endured. Today, researchers study them with extraordinary precision. They examine chemical fingerprints invisible to the naked eye. They compare elemental ratios. They analyze structures formed when Earth was still a very different planet. The goal is not to find a single dramatic answer. The goal is to recover fragments of a vanished world. Imagine discovering a message from an era older than multicellular life itself. Not a written message, but a collection of clues hidden within a crystal smaller than a fingernail. That is essentially what scientists are doing. Each sample contains hints. None contains the complete story. A single crystal might reveal information about ancient temperatures. Another may provide clues about the chemistry of long-vanished oceans. A different mineral may preserve evidence of atmospheric conditions existing billions of years ago. Individually, the clues seem limited. Together, they become powerful. This is where the investigation begins to resemble the assembly of a vast puzzle. No single discovery proves the existence of red oceans. No single rock contains all the answers. Instead, scientists combine evidence gathered from many sources. Clue from one continent supports evidence from another. Geology connects with chemistry. Chemistry connects with biology. Biology connects with climate science. Piece after piece begins fitting together. Process requires patience because deep-time mysteries rarely reveal themselves easily. Researchers must compare observations collected across decades. They must evaluate competing interpretations. They must determine whether patterns appearing in one location also appear elsewhere. The remarkable outcome is consistency. Again and again, independent lines of evidence point towards similar conclusions. Iron-rich formations appear where they should. Chemical signatures align with expectations. Ancient environmental conditions reconstructed through different methods often support one another. The strength of the argument emerges not from a single spectacular discovery, but from accumulation. One clue may be uncertain. Hundreds of clues become difficult to ignore. Realization changes the nature of the mystery. The evidence for ancient red oceans is indirect, yet indirect evidence can still be compelling. Human beings have never seen those vanished seas. No observer recorded their appearance. Yet the surviving traces left behind by ancient processes continue pointing toward the same extraordinary possibility. The oceans of the distant past may have looked fundamentally different from those of today. What makes the story especially fascinating is that each answer uncovers new questions. Every reconstructed environment reveals additional uncertainties. Every solved puzzle exposes another mystery hidden beneath it. The deeper scientists investigate Earth's earliest history, the more complex the picture becomes. The surviving evidence is remarkable, but it is not complete, and that leads to one of the most intriguing realities in all of Earth science. Even with these extraordinary tools, some mysteries remain unresolved, and the farther back researchers look into the ancient past, the more questions they discover waiting for them. For all that science has uncovered about Earth's distant past, one uncomfortable truth remains. No one knows exactly what the red oceans looked like. That uncertainty may seem surprising after decades of research. Scientists have analyzed ancient rocks, studied chemical signatures, reconstructed environmental conditions, and traced the chain of events that transformed the planet. The evidence supporting iron-rich oceans is substantial. The broader story is increasingly clear. Yet some of the most fascinating questions remain unanswered, and perhaps they always will. Earth's oceans truly red across the entire globe, or did the coloration vary from region to region? Did vast stretches of water appear deep crimson beneath ancient skies, or were the colors more subtle, shifting according to local chemistry, depth, and environmental conditions? No surviving witness exists to settle the debate. The further researchers travel into deep time, the more they encounter the limits of certainty. This is not a weakness of science. It is one of its defining strengths. Science does not claim to possess final answers simply because questions are difficult. Instead, it continually tests ideas against evidence, refining explanations as new discoveries emerge. Sometimes evidence strengthens existing theories. Sometimes it challenges them. Occasionally, it forces entire assumptions to be reconsidered. The mystery of the red oceans illustrates this process perfectly. Some scientists envision oceans with dramatic coloration extending across enormous portions of the planet. In these reconstructions, dissolved iron existed in concentrations high enough to create striking visual effects, especially under certain lighting conditions. Others propose a more complicated picture. Perhaps some regions appeared strongly colored, while others looked different. Perhaps ocean chemistry varied significantly from one environment to another. Ancient coastlines, water depth, volcanic activity, and biological influences may all have affected appearance. Possibilities remain under investigation. The evidence supports broad conclusions, but many details remain uncertain. And the details matter because they shape how researchers imagine entire worlds that no longer exist. What did a shoreline look like 4 billion years ago? What color did waves appear beneath a sunset? How transparent was the water? How rapidly did environmental changes occur? Questions like these capture the imagination precisely because they sit at the boundary between knowledge and mystery. The situation becomes even more intriguing when considering the limits of technology. Modern science possesses extraordinary tools. Researchers can analyze atoms, identify ancient chemical signatures, and reconstruct environmental conditions from tiny mineral samples. Yet no instrument can solve the most fundamental problem. No one can travel back in time. There is no direct observation, no photograph, no preserved recording. Every reconstruction remains an interpretation built from surviving evidence. Some interpretations become highly convincing, others remain speculative. The process resembles assembling a portrait from scattered fragments rather than viewing the original image itself. That reality does not diminish the achievement. If anything, it makes the achievement more remarkable. Scientists are attempting to reconstruct entire oceans, atmospheres, and ecosystems from clues that survived billions of years of geological destruction. The fact that they can say anything meaningful at all is extraordinary. Yet uncertainty persists. And that uncertainty serves an important purpose. It keeps the investigation alive. Every unanswered question becomes an invitation for future discovery. Every disagreement encourages new research. Every mystery creates opportunities for better evidence and deeper understanding. The story of the red oceans remains unfinished, not because scientists have failed, because the Earth still has secrets. Perhaps future discoveries will reveal details no one currently suspects. Perhaps hidden clues remain buried within ancient rocks waiting to be found. Perhaps entirely new technologies will uncover information impossible to extract today. The search continues, and that search leads to a broader realization. Earth's oceans, atmosphere, and landscapes once looked so different from the world we know, then the red ocean era may represent only one chapter among many forgotten versions of our planet. The question is no longer whether Earth changed. The question is how many different Earths have existed before the one we call home. People think about Earth, they often imagine a single world. The continents seem fixed. The oceans appear permanent. The atmosphere feels familiar and dependable. Even when people acknowledge that the planet has changed through time, there is often an unspoken assumption that those changes occurred around the edges of a fundamentally recognizable Earth. The deeper one travels into the past, the harder that assumption becomes to maintain. The story of the red oceans revealed one version of Earth that no longer exists. Iron-rich seas stretched across the planet. Oxygen was scarce. The atmosphere followed unfamiliar rules. Life consisted almost entirely of microscopic organisms. To modern eyes, that world would seem strange, perhaps even alien. Yet it was only one chapter. Earth's history contains many others. In fact, one of the most profound lessons hidden within geology is that Earth has not been a single world throughout its existence. It has been many different worlds sharing the same planet. There was an Earth where oxygen barely existed. There was an Earth where vast regions may have disappeared beneath ice. There were Earths where continents occupied positions that would appear completely unfamiliar. Today, oceans opened where land now stands. Mountains rose where seas once existed. Entire landscapes came and went without leaving obvious traces. Each version of Earth followed different rules. Each possessed its own atmosphere, climate, geography, and living communities. This perspective changes the way the red ocean era is understood. Rather than appearing as an isolated anomaly, it becomes part of a larger pattern. Earth's history is filled with transformations that would have seemed impossible to any observer living through them. Conditions that appeared permanent eventually vanished. Entire environmental systems emerged, dominated the planet, and then disappeared. The modern world is no exception. It simply happens to be the version humans know. That realization invites a certain humility. People naturally treat the present as normal. Modern oceans feel like the standard against which all others should be measured. Modern climates feel familiar. Modern ecosystems appear established and stable. Yet geological history repeatedly demonstrates that normal is a temporary concept. What seems permanent on a human timescale may be fleeting on a planetary one. Millions of years can transform coastlines. Tens of millions can rearrange continents. Hundreds of millions can alter atmospheres and ecosystems. Given enough time, entire worlds emerge and fade away. The Earth of today represents only a brief moment within a story extending more than 4 billion years. Countless chapters preceded it. Others remain unwritten. Perhaps the most fascinating implication emerges when imagining a traveler moving through time. Suppose someone could stand on Earth during different eras of its history. They would witness red oceans, frozen landscapes, oxygen-poor atmospheres, unfamiliar continents, and ecosystems unlike anything alive today. Some periods would feel so different that recognizing the planet itself might become difficult. The same Earth, the same world, yet transformed almost beyond recognition. This is not merely a story about environmental change. It is a story about planetary identity. Earth has never stopped evolving. Every age inherits conditions created by previous ages. Every transformation opens possibilities for new transformations. The world humans inhabit today exists because earlier versions of Earth repeatedly reshaped themselves. Red oceans helped create one such transition. The oxygen revolution created another. The frozen ages created others still. Each chapter influenced the next. Each world prepared the way for a future world. Seen from this perspective, Earth's history becomes less like a timeline and more like a sequence of interconnected realities. One planet continuously reinventing itself across billions of years. And that raises an unavoidable question. If Earth has repeatedly transformed into such dramatically different worlds, what forces are powerful enough to drive changes on that scale? Mechanisms keep rewriting the story of an entire planet. The answer lies within the hidden systems that connect oceans, atmospheres, continents, climate, and life itself into a single evolving machine. Earth has transformed itself again and again throughout history. What drives those transformations? The answer is both simple and astonishing. No single force controls the planet. Instead, Earth behaves like a vast network of interconnected systems, each influencing the others in ways that often remain invisible until millions of years have passed. Oceans affect climate. Climate influences life. Life alters atmospheric chemistry. Geology reshapes continents. Continents redirect ocean currents. Every component participates in an ongoing conversation that never truly ends. Nothing exists in isolation. That is the secret hidden beneath Earth's history. People imagine planetary change, they often search for one dramatic cause: a giant volcano, a powerful asteroid, sudden catastrophe. Such events certainly matter, but they rarely tell the entire story. The deepest transformations usually emerge from interactions between many different forces operating simultaneously. The era of red oceans provides a perfect example. At first glance, it appears to be a story about iron. Closer, and the picture becomes far more complicated. Geological activity supplied enormous quantities of dissolved iron to the oceans. Volcanoes and hydrothermal systems transported minerals from Earth's interior into seawater. Without those geological processes, the iron-rich oceans may never have existed. Yet geology alone cannot explain what happened next. Life entered the story. Microscopic organisms evolved the ability to produce oxygen. Their activity gradually altered ocean chemistry. Oxygen reacted with dissolved iron. Iron-rich waters changed. Atmospheric composition shifted. Climate responded. Each step influenced the next. The transformation was not caused by geology alone or biology alone. It emerged from their interaction. This pattern appears repeatedly throughout Earth's history. A continent moves. Currents change. Climate responds. Ecosystems adapt. New environmental conditions emerge. What begins as one event spreads through multiple systems, producing consequences that extend far beyond the original cause. Process resembles a chain of falling dominoes, except the dominoes are constantly interacting with one another. Sometimes a small change remains local, other times it expands until it influences the entire planet. Possibility is one of the most fascinating aspects of Earth science. Small causes can produce enormous consequences when given enough time. The oxygen-producing microbes that transformed ancient oceans were microscopic. Individually, they seemed insignificant. Yet their collective activity altered the chemistry of seawater, changed the atmosphere, influenced climate, and helped create conditions that would eventually support complex life. The scale of the outcome bears little resemblance to the size of the organisms involved. Geological time amplifies everything. Tiny changes repeated over millions of years become planetary transformations. This realization leads to a profound shift in perspective. Life is often portrayed as a passenger traveling through Earth's history. Organisms adapt to changing environments. They respond to conditions created by geology and climate. While this view contains truth, it is incomplete. Life is not merely reacting to the planet. Life is helping shape it. The evidence appears throughout Earth's past. Oxygen-producing microbes transformed atmospheric chemistry. Plants altered carbon cycles. Entire ecosystems influenced environmental conditions around them. Again and again, living organisms modified the world they inhabited. The relationship works in both directions. Shapes life. Life shapes Earth. Neither exist independently of the other. Perhaps that is the most remarkable lesson hidden within the story of the red oceans. Planet is not a collection of separate systems operating side by side. It is a deeply interconnected whole where geology, chemistry, climate, oceans, and biology continuously influence one another. The world humans know emerged from those interactions. So did every previous version of Earth. And if life possesses the power to reshape an entire planet, then a fascinating possibility emerges. Perhaps the same thing is happening elsewhere. Perhaps distant worlds orbiting other stars are being transformed by their own living inhabitants, just as Earth once was. If so, the lessons hidden within Earth's ancient red oceans may help humanity recognize life on planets it has never seen. For most of human history, Earth was the only known world. The stars filled the night sky with mystery, but no one knew whether planets existed around them. Entire generations looked upward and wondered if other worlds might circle distant suns. Question remained unanswered for centuries. Today, the situation is very different. Astronomers have discovered thousands of planets beyond our solar system. Some are giant worlds larger than Jupiter. Others are rocky planets that may resemble Earth in size. Many orbit within regions where temperatures could allow liquid water to exist. And wherever liquid water becomes possible, curiosity quickly follows. Because water raises another question. What do those oceans look like? Human imagination often assumes they must resemble Earth's modern seas. Blue water stretching beneath familiar skies, waves moving across coastlines, clouds drifting overhead. Yet the story of Earth's red oceans offers a powerful warning against such assumptions. Blue oceans are not inevitable. They are the result of specific conditions. Change those conditions, and an ocean may appear entirely different. Billions of years ago, Earth's own seas may have contained extraordinary quantities of dissolved iron. Oxygen remained scarce. The chemistry of the water followed unfamiliar rules. The result was a world that might have looked surprisingly alien, despite being the direct ancestor of the modern planet. Possibility expands the imagination. If Earth once experienced such a stage, perhaps other planets do as well. Somewhere among the countless worlds scattered across the galaxy, there may be planets rich in dissolved minerals. Some may possess atmospheres with very little oxygen. Others may be inhabited only by microscopic life forms, still beginning their own environmental transformations. To a distant observer, those worlds might look strange, yet they could be following paths remarkably similar to Earth's. Imagine a rocky planet orbiting a faint star. Its oceans contain large amounts of dissolved iron. Oxygen remains rare. Microscopic organisms drift through the water, quietly altering their environment. The atmosphere is different from Earth's today, but perhaps not so different from Earth's distant past. From space, the oceans may appear reddish rather than blue. The image sounds exotic, yet it may not be unusual. This is one of the most exciting ideas in modern planetary science. History provides a framework for understanding worlds that humanity cannot yet visit. By studying ancient environments preserved in rocks, scientists learn how living planets evolve through time. The lessons reach far beyond our own world. A planet that appears unfamiliar today may simply represent an earlier stage of development. What looks alien might actually be part of a common planetary story. Just as Earth transformed from iron-rich oceans to oxygen-rich skies, other worlds may be experiencing similar transitions, perhaps entirely different ones. That uncertainty is part of the wonder. The universe may contain oceans of colors humans have never imagined, green seas rich in unusual chemistry, dark oceans beneath thick atmospheres, purple waters reflecting unfamiliar sunlight. Worlds where biology and geology interact in ways that challenge every expectation formed from modern Earth. Possibilities are almost endless. Yet among all those possibilities, ancient Earth remains one of the most valuable guides available. Its red oceans demonstrate that habitable worlds can look dramatically different while still supporting life. Its history reminds scientists that appearances alone may be misleading. Planet does not need to resemble present-day Earth to be alive. That realization changes the search itself. Instead of looking only for worlds identical to our own, researchers can search for worlds resembling different chapters of Earth's history. Perhaps one day a telescope will detect a distant planet whose oceans still resemble the red seas that vanished from Earth billions of years ago. If that happens, the discovery will carry an extraordinary implication. What seems strange from a human perspective may actually be common throughout the cosmos. And the ancient red oceans of Earth may represent not an exception, but one chapter in a story shared by countless living worlds across the galaxy. Yet before looking too far outward, it is worth pausing to appreciate just how extraordinary Earth's own journey has truly been. Looking backward through Earth's history creates a powerful illusion. The story appears inevitable. Red oceans formed, oxygen-producing microbes emerged, the atmosphere changed, complex life eventually appeared. From a distance, the sequence seems almost orderly, as though the modern world was always destined to arrive. Yet history rarely works that way. The closer scientists examine the past, the more fragile the story becomes. Every chapter depended on countless conditions aligning at precisely the right moments. Every transformation rested upon foundations built by earlier transformations. Remove one piece, alter another, and the outcome might have been dramatically different. The Earth humans know today was never guaranteed. That realization begins with the red oceans themselves. It is easy to think of iron-rich seas as merely one stage in planetary development, but even their existence depended upon a remarkable combination of circumstances. Geological activity supplied vast amounts of dissolved iron. The atmosphere remained low in oxygen. The oceans accumulated minerals over immense periods of time. Change any part of that system, and the story shifts. Perhaps the oceans never become rich in dissolved iron. Perhaps they follow a different chemical path entirely. Perhaps the conditions that supported later transformations never emerge. Then came another unlikely development. Somewhere within those ancient oceans, microscopic organisms evolved the ability to use sunlight in a revolutionary way. The innovation seems almost simple now because its descendants dominate the modern world. Yet there was nothing inevitable about its appearance. What if it never happened? What if those organisms failed to evolve? What if the biological pathway leading to oxygen production never emerged? The consequences would be difficult to overstate. The oceans might have remained fundamentally different. The atmosphere might never have accumulated large quantities of oxygen. Entire categories of life familiar today could have remained impossible. The chain breaks, the future changes. The story becomes unrecognizable. Even after oxygen-producing microbes appeared, success was not guaranteed. Environmental crises followed, ocean chemistry transformed, climate shifted. Ice may have spread across enormous portions of the globe. Each challenge introduced new risks. Life survived. Survival was not certain. Imagine a slightly colder climate. Imagine a more severe environmental disruption. Imagine biological communities unable to adapt quickly enough. A different outcome remains entirely possible. This perspective transforms Earth's history into something far more remarkable than a straightforward progression toward complexity. It becomes a sequence of narrow passages. Again and again, the planet approached crossroads where multiple futures were possible. One path led here. Others did not. The realization creates a sense of tension hidden beneath the familiar world. Modern Earth often appears stable and inevitable because its existence surrounds us. Oceans fill the basins. Forests cover the land. Animals move through ecosystems that feel established and permanent. Yet every one of those realities depends upon a chain of events stretching back billions of years. The oxygen in the atmosphere, the chemistry of the oceans, the evolution of complex organisms, the existence of humans, each emerged from transformations that could easily have unfolded differently. Perhaps that is the most astonishing lesson hidden within the story of the red oceans. Appears ordinary today is the product of extraordinary circumstances. The modern world exists because countless geological, chemical, biological, and climatic events occurred in a sequence that allowed each subsequent stage to emerge. No single event created Earth as we know it. Instead, billions of years of interconnected history gradually produced the conditions surrounding us now. The deeper the story is examined, the more improbable it appears. Iron-rich oceans formed. Microbes transformed them. Oxygen reshaped the atmosphere. Climate responded. Life adapted. Complexity emerged. Each step depended upon those before it. Each could have failed. And if even one crucial link had broken, the Earth of today might never have existed. Possibility raises an even deeper question. How much of Earth's history resulted from necessity, and how much resulted from chance? Were these transformations destined to occur, or did coincidence play a larger role than anyone suspects? The answer may reveal something profound about the nature of worlds, life, and the future itself. The deeper scientists investigate Earth's history, the harder one question becomes to ignore. Was any of it destined to happen? At first the answer appears obvious. Physical laws govern the universe. Water behaves according to predictable rules. Chemistry follows established patterns. Gravity shapes planets. Geological processes operate whether anyone observes them or not. From this perspective, Earth's story can seem inevitable. Given enough time, certain outcomes might appear almost guaranteed. Yet another perspective tells a very different story. History is filled with surprises. Evolution discovers unexpected solutions. Rare events alter environmental conditions. Small innovations trigger enormous consequences. A seemingly insignificant change can redirect the future in ways impossible to predict beforehand. This tension between necessity and chance lies at the heart of one of science's most fascinating mysteries. The story of the red oceans illustrates it perfectly. Some aspects appear predictable. If large quantities of dissolved iron exist in oxygen-poor water, certain chemical conditions naturally follow. If microorganisms release oxygen into those environments, reactions occur. Physical laws do not negotiate. They operate consistently. In that sense, parts of the transformation seem almost unavoidable. Yet other parts appear far less certain. The emergence of oxygen-producing microbes was not guaranteed by chemistry alone. Evolution had to discover that biological pathway. The timing mattered, the environmental circumstances mattered. Countless variables influenced what happened next. A different evolutionary innovation might have emerged, or none at all. The distinction is important because it changes how the entire story is viewed. Perhaps red oceans naturally created conditions favoring oxygen-producing life. If so, the oxygen revolution may have been highly probable. Perhaps the innovation represented an extraordinarily rare event that happened to occur on Earth. Scientists continue debating possibilities like these. The uncertainty extends far beyond biology. Climate offers similar puzzles. Certain atmospheric changes predictably influence temperature. Yet the exact response of a planet can depend upon countless interacting factors. Geological activity fluctuates, and circulation evolves. Ice expands and retreats. Small differences sometimes produce dramatically different outcomes. The same pattern appears throughout Earth's history. Physical laws create possibilities. Chance influences which possibilities become reality. Neither force acts alone. Imagine standing at one of the great crossroads in Earth's past. The future remains unwritten. Multiple pathways stretch ahead. Some may be more likely than others, but none are guaranteed. A volcanic eruption occurs at a critical moment. An evolutionary innovation appears earlier or later. Environmental conditions shift slightly. The consequences accumulate. Millions of years, tiny differences become enormous ones. This realization encourages humility. Human beings naturally search for clear explanations. We prefer stories with obvious causes and predictable outcomes. History resists that simplicity. It unfolds through interactions so complex that even today researchers cannot fully separate necessity from accident. How much of the modern world was inevitable? How much depended upon unlikely circumstances? No definitive answer exists. Perhaps none ever will. That uncertainty is not a flaw in the story. It is part of what makes the story so compelling. The Earth we inhabit emerged from billions of years of interacting processes operating across immense spans of time. Some events followed patterns that appear predictable. Others may have depended upon astonishing coincidences. The exact balance remains one of science's great unanswered questions. Perhaps complex life was destined to emerge somewhere along Earth's timeline. Perhaps it was one of the rarest outcomes imaginable. Perhaps the truth lies somewhere between those extremes. Matters is that the story remains open. Even now, scientists continue exploring evidence, testing ideas, and refining their understanding of how the modern world came to exist. Mystery endures, and as the investigation approaches its final chapters, a deeper realization begins to emerge. The red oceans were never merely about color, chemistry, or ancient environments. They reveal something far more profound about Earth itself. Planet shaped by both order and uncertainty, where countless forces combine to create a world unlike any that came before it. 4 billion years is a span of time so vast that the human mind struggles to hold it comfortably. Civilizations rise and fall within thousands of years. Recorded history covers only a tiny fraction of humanity's existence. Even the oldest monuments seem recent when compared with the age of the planet itself. Yet the story of the red oceans stretches across those immense depths of time. And when viewed from beginning to end, it becomes something far greater than a mystery about ancient water. It becomes a story about transformation. The journey began with a world almost unrecognizable by modern standards. Oceans contained extraordinary amounts of dissolved iron. Oxygen remained scarce. Microscopic organisms drifted through waters operating under chemical rules unlike those of today. The atmosphere, climate, and ecosystems belonged to a planet that seemed more alien than familiar. Yet that world was not separate from our own. It was the beginning of it. Billions of years, one change led to another. Geological forces supplied iron to the seas. Tiny organisms discovered new ways of capturing energy from sunlight. Oxygen entered the water. Ocean chemistry shifted. Atmospheric composition evolved. Climate responded. Life adapted. The chain continued. The red oceans faded. New environments emerged. Complexity increased. Every chapter influenced the next. Looking backward, the connections become impossible to ignore. The iron formations preserved in mountains today are linked to reactions that unfolded in ancient seas. The oxygen filling modern skies traces part of its history to microscopic organisms living billions of years ago. Even the existence of complex ecosystems depends upon transformations that began long before animals appeared. Nothing exists in isolation. The present carries traces of the past everywhere. This realization changes the meaning of the red oceans. Early in the story, they seemed like a geological curiosity, an unusual possibility hidden within Earth's distant history. Now they appear differently. They become a symbol, a reminder that the planet humans inhabit has never been fixed or permanent. Again and again, Earth reinvented itself. Oceans changed, atmospheres changed, climates changed, life changed. Each transformation opened possibilities that did not previously exist. Conditions that seemed stable eventually gave way to something new. Entire worlds emerged from the remains of earlier worlds. The pattern repeats throughout the history of the planet. And perhaps that pattern is the most important discovery of all. People often think of Earth as a finished place, a completed world whose major chapters have already been written. Geological history tells another story. It reveals a planet in constant motion, continuously evolving through interactions between geology, chemistry, climate, and life. The Earth of today is not the final version. It is simply the current one. That idea carries a certain humility. Familiar landscapes surrounding modern civilization feel permanent because human lives are short. Oceans appear timeless, mountains seem immovable, the atmosphere feels stable, yet viewed across billions of years, all of these features are temporary. They belong to a particular chapter, a chapter still being written. Perhaps that is why the story of the red oceans resonates so deeply. It reminds us that the world we know emerged from conditions that once seemed impossible. Ancient seas became modern oceans. Microscopic life transformed the atmosphere. Environmental crises created opportunities for new forms of existence. A familiar world arose from extraordinary change, and change has never stopped. Final revelation is both simple and profound. Appears today as a stable, recognizable Earth is actually the latest expression of a planet that has spent billions of years transforming itself. The blue oceans humans know are not the beginning of the story. They are one moment within it. And if Earth's history teaches anything, it is that every chapter eventually gives way to another. The question is no longer what the oceans looked like billions of years ago. The question is what they might become in the future. Because the story of Earth's oceans is still unfolding, At the beginning of this journey, there was a simple but unsettling image. An ocean stretched to the horizon. The waves moved as oceans always move. The wind crossed the water. The planet beneath the sky was unmistakably Earth. Yet something felt wrong. The sea was red. At the time, the image seemed impossible. It belonged to a world so different from the modern one that it felt almost alien. The mystery invited a question that carried us across billions of years of history. Could Earth really have looked like that? Now, after following the evidence through ancient rocks, vanished oceans, oxygen revolutions, frozen worlds, and evolutionary transformations, the image carries a different meaning. It no longer feels impossible. Instead, it feels like a reminder that the familiar world is only the surface of a much deeper story. Every day, people move through landscapes that appear stable and permanent. Mountains rise above horizons. Rivers flow toward the sea. Clouds drift across the sky. Oceans stretch beyond sight. These features feel timeless because they exist within the brief span of a human life. Yet none of them represent the whole story. Each is merely the latest expression of a planet that has spent billions of years changing itself. The mountains standing today often contain fragments of ancient seafloors. The air filling human lungs carries the legacy of microorganisms that lived billions of years ago. The chemistry of modern oceans reflects transformations that began long before animals existed. Present is built upon the past. Quite literally, beneath every familiar landscape lie traces of forgotten worlds. Realization changes the way ordinary places appear. A rocky hillside becomes more than a collection of stones. It becomes a surviving fragment of deep time. A coastline becomes more than a boundary between land and sea. It becomes part of a story extending back through countless earlier coastlines that have long since vanished. World humans sea is layered, not only physically, but historically. Entire versions of Earth exist beneath the modern one. Most are invisible. The red oceans are gone. No trace of their waters remains. The coastlines that bordered them disappeared billions of years ago. The ecosystems inhabiting them transformed beyond recognition. Yet their influence survives. It exists in iron-rich formations hidden within mountains. It exists in the oxygen-rich atmosphere surrounding the planet. It exists in the chain of events that eventually allowed complex life to emerge. The oceans vanished. Consequences remained. Perhaps that is one of the most profound discoveries hidden within Earth's history. The most important events are often invisible. They do not announce themselves. They leave subtle traces rather than obvious monuments. Entire worlds can disappear while their influence continues shaping everything that follows. Modern humanity lives among those influences every day. Most people simply do not realize it. The ground beneath cities contains memories older than multicellular life. The materials used to build civilizations often originated in environments that no longer exist. Even the conditions making human existence possible emerged from transformations hidden deep within the past. Forgotten worlds surround us, not as ghosts or legends, but as physical realities preserved within the planet itself. The task of science has been to uncover those realities, piece by piece, from the fragments that survived. And what those fragments reveal is extraordinary. The Earth people today is not the end point of history. It is not the final version of the planet. It is one chapter within a story still unfolding. Earlier worlds prepared the way for it. Future worlds will eventually follow it. The red oceans were one of those worlds. The modern Earth is another. And somewhere beneath the familiar landscapes of the present, the traces of countless forgotten Earths remain waiting to be discovered. Realization invites a final reflection, not merely about the planet itself, but about humanity's place within the immense depths of time that shaped it. There is something humbling about deep time. Not because it makes humanity unimportant, because it reveals the true scale of the story we inhabit. Human beings naturally experience the world through short intervals. A year feels meaningful, a century feels historic, 1,000 years can seem almost unimaginably distant. Entire civilizations are measured within these spans. Kingdoms rise, flourish, and disappear. Languages evolve, cultures transform, generations come and go. Against the backdrop of human history, such changes appear immense. Against the backdrop of Earth, they are barely visible. The era of red oceans existed billions of years ago. The transformations that followed unfolded across stretches of time, so vast that the human mind struggles to comprehend them. Entire chapters of planetary history lasted longer than all recorded human civilization combined. The numbers themselves are difficult to grasp. Millions of years, hundreds of millions, billions. Beyond a certain point, the distinctions blur together. The imagination loses its ability to visualize durations so immense. Deep time becomes less like a timeline and more like an ocean without a visible shore. Yet those incomprehensible spans matter, because within them the foundations of the modern world were assembled. The red oceans existed long before animals appeared, long before forests spread across continents, long before human beings looked toward the horizon and wondered how the world came to be. And yet those ancient oceans helped shape conditions that eventually made all of those things possible. The connection is extraordinary. Events unfolding billions of years ago influenced the atmosphere humans breathe today. Ancient microorganisms altered planetary chemistry. Environmental transformations opened possibilities that later life would inherit. Every chapter built upon previous chapters, linking the distant past to the present through an unbroken chain of cause and effect. Realization can inspire a feeling of smallness, but it can also inspire wonder, because there is another side to the story. Humanity may occupy only a brief moment within Earth's history, yet humanity possesses something unique. We are capable of looking backward across those immense spans of time and attempting to understand them. No organism living in the red oceans could imagine the future. No ancient microbe drifting through iron-rich waters could foresee forests, animals, civilizations, or science. Billions of years later, a species emerged capable of reconstructing worlds that vanished before its ancestors existed. That achievement is remarkable. The same evolutionary process shaped by ancient planetary changes eventually produced minds able to investigate those changes. The universe created observers capable of studying the history that created them. In a sense, Earth's story became aware of itself. Scientists examine ancient rocks and recover traces of forgotten environments. Researchers analyze tiny crystals preserving information older than multicellular life. Entire disciplines work together to reconstruct worlds that no human ever witnessed. The task is extraordinarily difficult, and yet it succeeds, not perfectly, not completely, enough to reveal glimpses of histories once thought permanently lost. Perhaps that is one of humanity's greatest accomplishments. Not the construction of cities or technologies, but the ability to reach backward through billions of years and uncover the story of a planet that existed long before anyone was there to observe it. The red oceans remind us of that achievement. They remind us that knowledge can bridge astonishing distances in time. They remind us that curiosity allows human beings to explore not only distant places but distant ages. And they remind us that understanding the past deepens our appreciation of the present. The lesson is not that humanity is insignificant. The lesson is that humanity belongs to something far larger, a story billions of years in the making, a story still unfolding. And as this journey approaches its end, one final realization remains. For all that science has uncovered, for all the mysteries solved and clues assembled, a certain silence still surrounds the deepest chapters of Earth's history. The same silence that existed before anyone was here to ask questions at all. The story does not end. It softens instead. It becomes quieter, less concerned with answers, and more attentive to the vastness that surrounds them. After billions of years of transformations, after red oceans and oxygen revolutions, frozen worlds and evolutionary experiments, there remains something that no discovery has fully erased. The silence. It has been present from the beginning. Before the first microorganisms drifted through iron-rich seas, the silence was there. Before oxygen entered the oceans, before continents took familiar shapes, before any living thing possessed eyes capable of looking across a horizon and wondering what lay beyond it. The silence remained, and in many ways it remains still. Science has illuminated extraordinary chapters of Earth's history. Ancient rocks reveal traces of vanished environments. Tiny crystals preserve messages carried across billions of years. Entire worlds have been reconstructed from fragments that survived the relentless recycling of the planet. Yet every discovery reveals additional mysteries. Every answer uncovers new questions. The red oceans are a perfect example. They are no longer impossible to imagine. Evidence suggests they may have existed. Geological clues point toward iron-rich seas unlike anything visible today. Researchers have assembled a compelling story connecting ocean chemistry, atmospheric change, climate shifts, and the evolution of life. And still, uncertainties remain. Exactly how red were the oceans? How did different regions appear? Details have been permanently lost. The silence holds those answers. Perhaps it always will. Yet the existence of mystery does not diminish the story, it enriches it, because the story was never truly about certainty. It was about exploration. It was about following clues through deep time and discovering that the world is far stranger, older, and more dynamic than it first appears. The oceans outside humanity's shores seem familiar today. Their blue surfaces reflect the sky. Waves move across coastlines that feel permanent. The world appears stable, settled, complete. Appearances can be deceptive. Beneath that familiar blue lies a history few people ever consider. Modern oceans inherited their existence from earlier oceans. Those oceans inherited conditions from worlds older still. Layer upon layer of forgotten history exists beneath every wave. The red oceans are part of that inheritance. So are the microorganisms that transformed them. So are the atmospheric revolutions, climate crises, and evolutionary innovations that followed. Nothing emerged in isolation. Everything connects. The realization extends beyond Earth itself. If one planet contains such hidden chapters, how many others might exist throughout the universe? Perhaps distant worlds orbiting remote stars possess histories just as dramatic. Perhaps alien oceans have changed colors over billions of years. Perhaps entire planetary stories remain waiting to be discovered. Every world may carry its own mysteries. Every planet may possess forgotten ages hidden beneath its present appearance. Possibility transforms the red oceans into something larger than a geological question. They become a symbol of how much remains unseen, a symbol of how worlds change, and a symbol of how understanding is always incomplete. The deepest revelation of this journey is surprisingly simple. The story was never only about red oceans, it was about transformation. A planet filled with iron-rich seas became a planet with blue oceans. A world dominated by microscopic life became a world of forests, animals, and civilizations. Conditions that once seemed permanent vanished. New possibilities emerged. The Earth remained the same planet while becoming something entirely different. That process continues. Continents still move, the oceans still circulate, chemical cycles still operate, life still adapts, remains unfinished. And perhaps that is why the story feels so compelling. It is not confined to the past. It extends into the future. The same forces that shaped ancient oceans continue working today. New chapters are already being written, even if no one yet knows their outcome. The blue oceans visible now are not the end of the story. They are one moment within it. And deep beneath their familiar surface lingers the memory of another world. World of iron-rich seas, silent microbes, planetary transformations, and mysteries echoing across billions of years. The silence remains, not empty, not forgotten, but filled with stories still waiting to be discovered. And somewhere within that silence, the story continues.